In this video, I will be carrying out the double slit experiment that was originally done by Thomas Young in the year 1801 to demonstrate the wave nature of light. This experiment includes shining laser light through two narrow slits that are spaced closely together. We normally think of light as a collection of particles. By shining a flashlight through a slit, we can see that light travels in a straight line and shines on the wall, as a particle would. Now what if we swap out the flashlight for a red laser? And instead of using one big slit, we use two close and narrow slits. Two close and narrow slits are cut in a piece of aluminum foil and a red laser is shown through it. By shining a red laser through the slits, an interference pattern appears. We can see an interference pattern which is caused by the light waves passing through the two slits interfering with each other. The patterns are caused by two types of interference, constructive and destructive interference. The visible lines are the constructive interference, and the spaces between the lines are the destructive interference. Constructive interference occurs when two waves are in sync with one another so that both peaks arrive at the same time and intensities add. Destructive interference occurs when two waves are exactly out of sync with one another so that the peak of one corresponds with the tuff of another and they both cancel each other out. It can also be observed that the middle line is longer and brighter than the neighboring lines. This is because when light diffracts, it spreads out and is brightest at the center. Now let's see if the phenomena we just observed will also happen with a green laser. Using the same two slits, instead of a red laser, a green laser is shown through it. After aligning the laser lights with the two slits, we can observe an interference pattern similar to the one made with the red laser. As we can see, we then get the same effect as the red laser. However, the bright spots are closer together. As was mentioned before, the visible lines in the interference pattern are the constructive interference. We can find the constructive fringes when d times sine theta equals to m times lambda, for m equals 0, 1, 2, 3, and so on. Where d is the distance between the two slits, theta is the angle from the perpendicular or the normal, and lambda is the wavelength of the laser. On the other hand, the destructive interference is the space between the visible lines. We can find the destructive interference by using the formula d times sine theta equals to m plus a half times lambda, for m equals 0, 1, 2, 3, and so on. Where d is the distance between the two slits and theta is the angle from the perpendicular or the normal, and lambda stands for the wavelength of the laser. If m equals 0, then sine theta equals to 0 as well. Therefore, theta equals 0, which is at the perpendicular or at the normal. Let's try to calculate theta for the first constructive fringe. Assuming that the distance of the two slits was 1 millimeter, we can plug 1 millimeter into d. Lambda stands for the wavelength of the laser, so we plug in 640 nanometers, because red laser has a wavelength of 640 nanometers. Next, we convert 640 nanometers into 0.000640 millimeters and take the inverse of sine 0.000640, which is 0.037. So, theta has a value of 0.037 degrees. Now, let's calculate theta for the first constructive fringe for a green laser. Using the same two slits, we can assume d has a value of 1 millimeter. A green laser has a wavelength of 530 nanometers, so we can plug that into lambda. Next, convert 530 nanometers into millimeters, which is 0.000530 millimeters, and take the inverse of sine 0.000530, giving us 0.030. Therefore, theta has a value of 0.030 degrees. We can conclude by comparing the two values of theta, which is 0.037 for the red laser and 0.030 for the green laser. that the green laser has narrower space between the lines. So you can see that we use some readily available and inexpensive material along with some simple geometry and basic properties of waves to understand the wave nature of light. I hope you enjoyed and found this video helpful. Thanks for watching!